Okay, let's get started. So this lecture is about HTTP outcalls and how to connect your canisters to a Web2 services or Web2 API. The, the problem of connecting blockchain services and smart contracts with the external world is a problem that has been around since the beginning. Essentially, the issue is that when you're on chain, so if you have one smart contract, you can easily talk with other smart contracts, but it's really hard to get information from the outside. So let's imagine we have a contract. In this case, it's know the weather, for example. We need to know if there was a drought or a flood or something. And so in this case, it's very hard to get that information into the chain. There are some solutions. The most important solution and the most used right now, it's something called an oracle. Chainlink, which is you can see the logo here in the middle, is probably the most used oracle. Essentially, Chainlink is going to call the API of the service. So in this case, the weather API, get the information that you want, and then write that to a smart contract on the chain. So let's say on Ethereum, and then your contract, so smart contract. So as you can see, it introduces a new parameter. So if you're building your application like this, you essentially have to trust them. So it's pretty expensive to have this kind of setup. And also, it doesn't really work well for some scenarios. Like, for example, if you just want to call external service, so if you just, there is a lag. Is there a problem with my sound? 1 2 1 2. Is it right? Might be my connection. So where did it cut?
It's just sometimes good, but sometimes it cuts out. So
Okay, maybe I need to speak closer to the mic. So I was saying that it doesn't really work for some scenarios if you just need to call an API because you want to interact with a service. Like if you want to just ping something, it doesn't really work well because you can only do it by putting information. So that's the approach for most blockchains out there. On the internet computer, it's different. So it's a native approach. Essentially, oops, sorry. Let's see. Okay. So yeah, it's like this. So on the internet computer, it's a native approach. So canisters can directly make HTTP outcalls. Essentially, it's how you can see it on the image. It's as simple as calling the management canister and doing HTTP request. Then you have to provide, of course, the request, so the parameters for the request. But it's one line and it works like this. And so you can call any Web2 services. You can interact with a weather API or Coinbase or any kind of service that you want. So yeah, it looks like magic. So let's dive a bit into it, how it works. Sorry for the schema. I thought it was ready. Yeah. So step one, whenever you do this, essentially what's happening is that all the nodes are going to call the API under the hood. This is step one. Then they receive an answer. In step two, they have to come to a consensus on this answer that they receive. And we'll see a few cases after that where it can be a bit tricky. But essentially, let's say they all receive the same weather. They receive sunny. Everything is good. And then you receive the answer into your canister. It's a synchronous call, so you have to wait. But whenever the nodes come to a consensus on the result, they include that in the block, and essentially there is a callback, and it just calls your canister and resume the execution of the logic that you had. So pretty simple. The only thing that is complex and that has been solved by the protocol and by Definity is how to reach consensus. So on the left, we can see a pretty simple scenario. So it's essentially you have all the nodes that call and they all receive the same information. So in this case, the weather is sunny, and there is a storm. So as long as 2/3 of the nodes, so essentially the consensus, have the same information and they can reach a consensus, it will be the accepted information, even if there is one or two or several nodes that are malicious and try to, of course, change the results. As long as you have the consensus and they have the same information, it works like this. On the right, it can be a bit more complex in some scenarios. So essentially, if you're calling a service and there will be a slight latency with the nodes because each node is going to receive an answer at different time. And it might be that the result that you get is almost the same, but not the same. So let's say you receive the temperature, you're asking for the temperature, and you receive 27.25, 27.26, and 27.24. You essentially, as we can clearly see that it's the same result overall, but for the nodes, it's not going to be exactly the same. And so that's why there is a function that you can add to your request. It's called the transform function. And essentially, this function is going to be used as an input to make sure that you can reach a consensus. So for example, what you could do is you could use a truncate function. So you only want to keep the first part of the value. And so in that case, the consensus would be reached easily. It would be 27 degrees, and that's the value you would be returned. Another case where it can be an issue is like if you have a timestamp in the requests and the timestamp is returned, it might not be exactly the same because of the delays between nodes, and so you have to maybe remove it, only keep the part of the request that you're interested in, and so on. You could also do an average of the requests. It's up to you. But yeah, that's essentially all the scenarios you would see. So the use cases are very, very large. Essentially, HTTP outcalls have been live on the Internet Computer for 1 year, I think now, almost 1 year. And it enables a lot of new use cases that were not possible before. So there is one very straightforward use case that was built by Definity. It's a exchange rate canister. So it's a canister deployed on the mainnet. And this canister just gives you rates for all the major currencies. So you can, for example, get the rates of ICP to US dollar, for example, if you're interested. And the exchange rate canister behind the scene is going to call the major exchanges, so like Coinbase, Kraken, Binance, get the price of ICP, do some average, and store that value inside. There is another use case which I already talked in some session. You could essentially talk with IoT devices. So there is a project called Omnia Network, which essentially is trying to do that. You could talk with Ethereum. So you could use HTTP requests to directly talk to Ethereum nodes, for example. I think there is an example in Hazel. And also the upcoming Ethereum integration will be based on HTTP outcalls. You could also talk with social media, so Web2 social medias. In Web3, we usually like separate. We say Web2 social medias are very, very bad. We shouldn't use them. But I think it's a spectrum, and it's also great to be able to have Web2 interactions within Web3 services. Payment gateways. So we have cryptos, but we can also add traditional payment methods. So for example, you could use something like Stripe. And the last one, which is very exciting, is artificial intelligence. So you could have maybe on-chain, off-chain models running outside of the IC, and you could get the input or the output of the model and bring that inside a canister and do all sorts of things. So that's about it for the HTTP outcalls. Now Jordan is going to explain how exactly it works and how you can use it for your project.
All right. Okay, so yeah, that's HTTP outcalls. How do you actually program them in TypeScript? This information is available. It's a little bit sparse in the book for now. We've covered a lot of the heavy material, but these sections are works in progress still. But if you go to the management canister in the reference, 20.7.10 gives you an example of how to use the HTTP request functionality. There are also two very specific examples in the example repository. Again, I'll show in case people are only watching this video. But in the ASL GitHub repository, there is an examples directory with tons of examples. So the Ethereum JSON RPC and the outgoing HTTP requests are good examples for this. So how do we do this? Well, it's simple. We're going to make an update call. We're going to import the management canister. Remember, everything comes from the management canister. You're doing any kind of cross canister call. Well, when you're doing any kind of a special functionality like this, and HTTP request happens to be modeled after a cross canister call, it's going to be an asynchronous function called like outgoing HTTP request. Okay, in this case, we'll see. Maybe we'll return a string of the result if we can. So how are we going to do this? If we're just going to hard code everything to have a very, very, very simple example, then we'll just say our result is going to equal the management canister dot, look for HTTP request, and then we're going to pass in an object that has the request information. We're going to call dot call. So what do we got here? First, your URL. So I was looking for some simple APIs just to play around with. We can use this JSON placeholder. So this is just like a fake API that's actually live. So if we just curl this, it just returns this fake JSON object. So nothing crazy. Put that in as the URL, and then you just follow the information. We'll do the simplest thing possible. So for max response bytes, we won't discuss that yet. We'll just set it to none. Method. In this case, we're going to do a GET request. Now the types of methods that are available, let's just go look at this real quick. You can do GET methods, head methods, or post methods. Those are what are supported currently. Then you can pass in your headers. In this case, there are no headers required, so we'll just pass in an empty array. You put in your body as, I believe, a UTF-8 encoded UN data array, basically. But in this case, we don't need a body. We're just doing a GET request. And then you put in a transform function like Seb talked about to transform. It's a function that every single node is going to run to transform the response in case there could be differences in the responses. That transform function will make sure you need to program it to make sure that every single response will be the same on every single node. But to keep it simple for now, we'll just set it to none. Okay, so far, super simple. And then we are going to have to send some cycles with this. So we're going to add cycles. In this case, it's kind of hard to tell exactly how many cycles you'll need. So we will talk about pricing. If you go to the Internet Computer documentation and to the HTTP Outcalls technology overview, there is a section called pricing that explains, in a lot of detail how to actually do the pricing. Also, if you go to the gas and cycles cost section on the Internet Computer, go down to the table, there is an HTTPS outcalls section as well. So you could try to kind of manually figure all that out. But if we just send like no cycles, I'm hoping that it's going to basically tell us how many cycles that we need. So, but that's it. This is the basic, most basic response, I guess. Or this is the most basic request that you can do. This is a cross-canister call, so it's going to give us a call result. And the result, well, actually, is it a call result? Let's see exactly what it is. It is a call result, yep. With an HTTP response, we can go look at that type. It's going to give you the status, for example, 200, 404. It's going to give you all the headers, and it's going to give you the body as a blob. And again, blobs are uint8 arrays. If you want to see what headers look like, it's just a simple record with a name and a value. So it's all relatively simple. Again, we want to match on a result and handle both the success and the error case. So this will actually be the HTTP response in the OK case. And in the error case, should be a string. Yep. So in this case, actually what I'm going to do is for now return a blob. We will have to decode that. So in this case, we'll just return body. And then we could always log. Maybe we could just log the whole thing. I see that. Let's log the status. That'll be good. And then in this case, we'll just trap with this error. Okay. Very simple. Let's see if we can deploy it and actually get to work. So to go over this again, HTTP requests, you initiate them with a method on the management canister. You put in your URL. You should specify the max response bytes, but we have set it to none. And we'll talk more about pricing soon. This is all about pricing, the max response bytes. Methods, you have 3 to choose from. Get, header, post. Headers, it's an array of records with a name and a value. In this case, we don't have any headers. In this case, our body, we don't need one because it's just a GET request. So we're just passing none. And our transform function, technically speaking, because we are running just one replica, because it's local, I don't think I need a transform because there's no chance of it not coming to consensus. But we'll show you how to write a transform. Okay, so let's execute this. In the best case, this will actually work. Oh, perfect. No. So this is what I was saying. We sent 0 cycles with the request, right? Right here. I said 0. Well, luckily, it told me exactly how many are required. So I'll just copy that. Throw it in. And in this case, this should work because the size of my, so we did that curl, right? This is going to be the same data every time. I think there technically could be some differences because the headers coming back and everything could slightly change. So it's probably best to round this up to something a little more reasonable, like maybe 16 billion or something. Let's see if this works. Oh, that's so cool. So yeah, here's the blob. And I mean, apparently you can see the, I think it's because the blobs are UTF-8 code points when they're displayed. So we can actually kind of see the response here, which is awesome. And then if we go over to the replica, we should see that, remember we printed the status, so the status is 200. So not too bad. now, well, okay, maybe I should pause here before we dive in deeper. Are there any questions so far? No questions yet? Okay, then let's deal with the pricing just a little bit more, and we'll talk about max response bytes. So again, this pricing section is probably the most important thing for you to read if you want to figure out the price. If you want to figure out in extreme detail exactly what's going on, then you can look at the formula here. So they have their total cost split up into the scaling factor and the HTTP outcall cost. The scaling factor would be your subnet size divided by 13. So if you're on an application subnet, I believe your scaling factor is just going to be 1. And then the bigger you get, the more expensive it'll be. And then the actual HTTP outcall cost is going to be your per call cost. I believe you get your per call cost over here. Yeah, HTTPS outcall per call. So I believe it'd be for a 13 node subnet, 49 million cycles plus per request byte cost. Again, that's right here, HTTPS outcall request message size per byte. So 5,200 cycles per byte times the request size. The request size is right here. You take the length of the URL plus the length of your transform name. Remember, the transform is going to be a function that we hook up right here, which we haven't done yet, plus the transform's context length. So this transform, right here, HTTP transform, not only does it have a func, but it also has a context, which is a blob. So the length of the blob, plus the length of your body, plus the header length, and then the header length is found here. You just add up, I assume, yeah, the size of, you just add up the size of the names and the values of every single header. So that's the, I guess, hopefully official formula if you really want to get into it. But you might want to just do some heuristics to figure it out. So first heuristic was just set this to 0, right? And that gave us this. The problem is if your body is going to vary a lot, I mean, I don't know exactly how you'll deal with that. You will just need to decide what the maximum will be. If you don't set max response bytes, then it's going to set the maximum as 2 megabytes, which is the message size limit for ingress messages. And the problem is that that's going to be extremely expensive because it's basically going to be 2 megabytes. So 2 million bytes, I believe, times whatever the cost is per byte for that piece. So that could be very, very, very expensive. So this is the most expensive that you could get. So you want to figure out, well, okay, how big is this response actually going to be? So, I mean, this should be very close, but if you do want to do an alternative analysis, you can just do curl cache. There might be better ways, but you can look at the response headers, for example, and you can look at the content length response header. So that tells me that the body at max is going to be 292 bytes. So then I could use that information to help calculate this. What I like to do, though, is, I like to just kind of round it up. So that's what it gave me locally, and that's, and I just like to round up when I'm just prototyping, at least. So if we did want to set the max response bytes, though, what do we find in content length? 292. So, I mean, assuming that this will always be the same, I could just set it to 292, but I don't know. Maybe I know that JSON could change slightly, so maybe I could say like 500. Hopefully you understand, the point. It's just like in the stable structures from the the other lesson that we had, you need to just kind of come up with heuristics and reason through how big that needs to be. I'm hoping they can get rid of the need to do max response bytes, because I feel like that would make the API just a lot nicer to work with. So there you go. Let's deploy that, see if that works. And then headers, like we talked about, these are just records with a name and a value. Obviously, this would be an empty one. I don't remember. Yeah, okay. So let's say I wanted to set the host to something else. Host, I could call it like IC. Then you'd know it's coming from a computer canister. Maybe I could even do something crazy like IC canister and like set the actual canister's ID as the host. That would be kind of cool. So that's how you would do headers. Let's see if our request will work with our new max response bytes. Ooh, yeah, okay. So the problem is, I guess it's the entire response, including the headers. So it's probably a lot bigger than that. I mean, I don't know the best way to go about finding the entire size of your response at this point, but yeah, I don't know if I'm not sure the best way. So you could check through all this documentation and maybe they have something. But point is you need to find a reasonable maximum here. I'll just set it for back to none for now. Headers, okay. Body. In this case, you would need to basically encode as UTF-8. So let's say you wanted to do like a JavaScript string or something, or like a JSON string. Let's say you were doing some JSON API, right? So I don't know, you have some ID, some name of some API that you're calling, like an Ethereum API, like I don't know, read block or something. You can create your JSON object. What you'd want to do is then turn this into a string. So I'd stringify it. Then you would want to encode this. So you need some kind of UTF-8 encode function. And then, I mean, that'd be it. I can show you from the outgoing HTTP request example. Oh, there's no body in here, but sorry, it must be the Ethereum example. Yeah, notice we are using these two npm packages, encode UTF-8 and decode UTF-8. And in this case, this HTTP request is going to an Ethereum public Web2 API. So someone is running Ethereum infrastructure like Infura or QuickNodes or something. And we're just going to hit their endpoints. And notice right here, we just create a uint8 array. We encode the string of the JSON object. In this case, it's just the JSON RPC API. So just JSON, turn it into a string, encode it as UTF-8, and then send that in as the body. So body, not too crazy. Now let's talk about the transform. So again, the transform is to help with determinism. Every single node is going to execute the request. So when your response comes back, you need to ensure that that response is going to be the same on every single node. So what you do is you provide a function that those nodes can call. And I believe, yep, it's just a query function. So in this case, we're going to export a query function. We can just call it transform. The args will be special HTTP transform args. And it will return an HTTP response. So the args have a response property already. So we go with the shape of this. Remember, it has status and headers and body. We're just going to spread that in to an object. But let's go look at the transform args themselves. Basically, it's just a response to the context. What you're going to want to do is manipulate anything that could be different. So in this case, we don't care about the headers at all, right? I mean, this is just a contrived example, right? But if all you care about is the body coming back, and you know that the body will be deterministic, then why keep the headers around? So in this case, we'll just blow those headers away. And hopefully, I mean, it's a very, very simple transform function, but hopefully once every node executes this, then they'll all get back a pristine, just that JSON body that we're looking for, while ignoring the headers and all that stuff. And I mean, the status should be the same amongst all of them. And as long as there's nothing in the body that we would need to change, then this should be good. If there's something in the body that you need to change, then you would probably convert this back into a string, and you'd have to do your own manual string manipulations to remove things that you don't need. Then we hook up our transform by saying up.sum, and in this case, it's a func, and remember that funcs are tuples, which is just an array with two properties, or two elements. The first element will be the ID of the canister with the function. So in this case, we want to put our ID in, and then it would be the name. And so we'll just call it transform. Let's see what we did wrong. Oh yeah, we need the context as well. All right, the transform isn't an object with the func, and then with context. And yeah, we don't, in this case, have any context to pass along, so let's put it as empty. So there we go. This won't change the behavior of our thing because there's only one node, so it doesn't really matter locally, but when you deploy it, that's kind of the sad thing from my experience with HTTP requests locally. They seem to be quite a bit different than in production. Like, I don't know of a way to test your transform function besides actually pushing it to production and seeing if it works, basically. So hopefully I'm mistaken on that, but I don't know of another way to do it. So yeah, I mean, that's the basic API. You just perform HTTP requests. Some things to keep in mind. These take a few seconds. I mean, I would just say plan on like 5 to 10 seconds for these to return is good. These aren't going to be returning as fast as you would be used to on something like AWS or Google Cloud, right? It's not going to just be instant. Hopefully in the future they can reduce that latency. It will probably be pretty hard. I know there's something called like reduced quorum that I saw in the documentation, where in the future we might be able to choose like how many nodes we care about returning the correct response, because sometimes you might just, I mean, not all data needs to be 100% secure and go through consensus, right? Like, for example, talking over this video call, I mean, if some of the packets get lost, it doesn't matter because you're going to get the gist of what I'm saying. But in other cases, you want things to be 100% secure as much as possible. So I think a reduced quorum would allow us to deal with stuff like that. And this is the nature of I guess limitations and issues with the internet computer. Networking compared, it really depends on what you're comparing it to, but when we're comparing the internet computer to cloud platforms, there's a lot of capabilities that are missing, and networking is really not very strong. But when you compare the internet computer to other blockchains or decentralized computers, then these capabilities, I think, are quite fantastic and absolutely amazing. So, yeah, I mean, that's the basic API. There are two main examples in the repo, Ethereum JSON RPC, which does show you how to talk to one Ethereum node. This will get the balance. It's just using the JSON RPC API that gets the balance of an address, the earliest possible balance. Then over here, we are getting a block by passing in the block number. And then there's another example which shows you just how to go to get a like a normal JSON API, just using the XKCD API. Again, simple. It also shows you how to do it raw. I don't recommend doing things with the raw candid. You don't have to, but it is a possibility. You can just basically pass in candid bytes if you want to. Sometimes if you don't have typing information or you want to be maybe like some kind of proxy or something, you might need to do this, but just know that the capability is there. And then what's really cool is if we go back to the Ethereum example, okay, so here's what's quite amazing about the HTTP outcalls functionality. So there's already really good infrastructure for talking to Ethereum nodes that people provide over Web2 APIs, like Infura, like we talked about. But if you only rely on one Ethereum endpoint, then obviously there's a centralization risk there. But what's awesome is that the internet computer with this HTTP outcalls functionality, it's providing us general purpose HTTP request functionality essentially. So what you could do to make Ethereum communication more secure is just send off like 3, 4, 5, whatever requests at the same time to as many independent Ethereum node operators as you want. And you can even run your own Ethereum infrastructure and provide that as one of the endpoints as well. Send all 5 of those requests out, and then when they come back, just compare them. And I mean, I feel like that would be extremely secure. Not to mention that, I mean, and that's how Ethereum or Dfinity and the internet computer are going to move forward with the first phase, basically, of the direct Ethereum integration between the internet computer and Ethereum. It's going to be using HTTP outcalls under the hood. But later, hopefully by Q1 2024, that'd be nice. We're going to actually get rid of the, just Web 2 API underpinnings there. And I think it's going to use a very similar architecture, but we'll basically just talk to Ethereum nodes running alongside the replicas. So I guess I'm not sure that exactly ties in here, but just know that that's coming. And I wonder if under the hood they are using a similar HTTP request functionality to come to consensus on all that stuff. And I did want to point out some caveats that I think would be good to know about. Known limitations. Okay, responses must be similar. We already talked about that. We need to hook up a transform function to make sure everything's deterministic. Post requests must be idempotent. Imagine you have a post request. Post requests are designed to actually change something on the server that you're calling. So if you send off 13 post requests, your server might change that data in 13 ways. Let's say that the server is like, counting something or sending a notification. Well, if you receive 13 requests to send a notification, then it might send a notification 13 times. So what you really need is for your server to implement idempotency. There is an HTTP There's an HTTP request header, I believe, called like idempotency key that will allow you to send a unique identifier with all of your post requests, so that if the server sees that same header on multiple post requests, it will basically ignore it all but the first one. But not all servers implement idempotency, and so this could be an issue that you would have to deal with. I guess compromised. Yeah, oh, okay, that's interesting. So what I'm guessing from this would be, the problem is that if you have 13 nodes all sending post requests, it sounds like if there is a malicious replica, then it could actually change that post request and send it. Because I'm not sure how the replicas can come to consensus. Like when the replica is about to actually send that request, I mean, the server doesn't have any information about the consensus and such. So I haven't thought about this one too much, but I guess keep that in mind. This problem will not be there for GET requests, as far as I know. So it seems like it will just be for post requests. Also, the API is IPv6 only. So I know they're trying to get IPv4 to work, but if you're calling some URL that is only running over IPv4, then you just won't be able to do it. Also, you might run into problems with rate limiting if the server you're calling sees like 13 requests all within like 1 second, then it might think you're trying to DDoS it. So keep that in mind. And then we were talking about reduced quorum earlier. It's under future extensions. So IPv4 support is hopefully coming. And then here's reduced quorum. Canister can define that a reduced quorum should be used for requests. E.g. only one replica of the subnet making the request instead of all n replicas. Yep, that's exactly what I was saying. Oh, cool, and that could help the idempotency issue, but it wouldn't help the malicious canister issue. So there you go. I feel like their documentation is going to be very good on this. You can look at a few examples in the ASIL examples repo, and also this example is out of date, but so some of the syntax has changed, but you can actually see how to basically talk to multiple different Ethereum endpoints, basically compare their results, and basically come to consensus on multiple Ethereum endpoints. So this was designed to talk to the Ethereum blockchain and actually read the Chainlink smart contracts. So, but it could work for general purpose state basically. So that's what this example does for you. Let's see if I can show you. Might be in here. Oh yeah, this is quite old, but these are using generators. But the purpose is basically I fetched the, let's see, fetch latest answer. Anyway, there's a lot of code in here. I have to look through it again. But yeah, you can see us actually talking to the Ethereum protocol. And I believe, yeah, see provider URL. So I believe we provided multiple provider URLs and then came to consensus on all those results. So yeah, there you go. Happy to answer questions.
We had a few questions. So the first one, I think we answered it, but is it possible to make the HTTP outcall with only one node?
No, but that's what the reduced quorum functionality would let you do. So in the future, hopefully, yes.
What happens to the excess cycles if you put more cycles to the call?
Nope. Well, Okay, that's a good question. I think if you put too many cycles, I believe it will refund the cycles. But if you set your max response bytes too high, it's not going to refund that. It will charge you that entire thing. So that's my current understanding of that. But you could test that somehow locally. The problem is testing all these cycle things is just not very straightforward. But you'd have to maybe experiment with that a little bit. But I think it would refund you the cycles if you put too many cycles, but not if you put max response bytes too high.
Could you share the code? Some people ask if you could share it on GitHub. So maybe I don't know if you want to add it to Hazel, or you could also add it to the
Sure. Which
bootcamp
code?
repository. The one you did the demonstration with. I think it was at the
Yeah, I mean
45 minutes mark. So
that code. So the Ethereum JSON RPC example and the outgoing HTTP request example, they're like exactly what I just showed you. So like this is the same thing. So
okay, so it's already on Hazel.
sorry, I thought I was sharing my screen. I should just keep sharing. Yeah, just look at the outgoing HTTP request example. This is exactly what I showed you. I just used a slightly different API and actually put in the correct max response bytes. And here's your transfer function, and here's the API. So it's basically identical to what I showed you.
Okay. How do you pass parameters like API keys?
You put those in the headers, or you put that in the URL, or you put that in the body. So however the server you're hitting wants that information. So I believe probably the URL or the headers is what would happen. But that's a good question. I assume that the URLs allow query parameters and that they wouldn't change those, but I'm not sure. So you have to try that out.
If an application is very intensive in HTTP outcalls, should I pass some of them to the front end?
Yeah, I think you should do as much on the front end as possible because front end HTTP requests are basically free. In fact, they are free relative to you as a developer because you don't have to pay for the user's front end. So do everything on the client that you can, but some things for security purposes or for like availability purposes, like if you're calling a Stripe endpoint at a certain time or like have subscriptions, then you would need to do it in the canister.
Cool. I think we did all the questions. If I skip one, please let me know. Some of them were, I think, answered during the talk. I remember that we said we would talk about Hazel compared to like Rust and Motoko. So we
Yeah.
still have time for that?
Okay. Sure. Okay. So I'll stop sharing for this. So yeah, someone was asking in the last lecture, what can Motoko do that Hazel can't do? So let me give you a general overview, and then I guess we could talk about specifics if I can remember them. But basically, all of the CDKs, at least Rust, Motoko, Hazel, and Kybra, are generally very feature compatible. Like they're all doing the same things. They all have the same access to the IC API under the hood. And the IC API, if you do want to know about that, I'll drop this link in. If you go to the Internet Computer Specification, see if I can find it. And I'll post this link. Here we go. Basically, this is the functionality that the Internet Computer provides. If your CDK allows you to do all those things, then you're like a full-featured CDK. So Yeah, I just posted the link. You can go look at this stuff. So Azel, I mean, it basically has almost everything. And the thing is that Motoko and Rust and Azel and Kyber, like, they don't all have 100% of the features of all the other ones. So there are some things that Motoko can do that Rust can't do. There's some things that Rust can do that Motoko can't do. And there's things that Hazel and Kyber can do that they all can't do either. So generally speaking, I don't know if there's hopefully that makes sense at a general level. Okay, now you can think about speed, efficiency, security, and stuff like that. Motoko is the absolute most efficient CDK that I know of. I haven't seen benchmarks for the C++ CDK, so I mean maybe that could be better, but I don't think it will. But Motoko seems to be absolute best at the cycle efficiency, at least in some cases. So you have that. Also, Motoko has these stable variables. Like you can actually mark your variables as stable, but those have the pre and post upgrade serialization and deserialization issues still, I believe. So you have that to worry about. Motoko doesn't have access to any libraries unless they've been created by the Internet Computer community, and hasn't been around for that long. So Rust, Azel, and Kybra have access to basically all Rust crates. Azel and Kybra, you can write plugins to uh, Rust crates, and then Azel has access to npm packages, not all npm packages, but it does have access to npm packages, and Kybra, the Python CDK, sorry, has access to PyPy packages. So that's just an advantage that Motoko doesn't have, for example. As for security, I mean, I would say Rust is probably the absolutely most hardcore secure language that you'd be writing with because of how long it's been around. Motoko maybe would be second after that because of the amount of resources Tiffany has put into making it secure. And then you'd have Azel and Kyber after that because we're using more experimental technologies. Though Azel, we're doing a lot of re-architecturing under the hood right now, and we're thinking we're going to have a way more robust version of Azel coming out relatively soon. So you have that to think about. Then you have efficiency. We talked about efficiency, so Motoko is probably best, then Rust. And then Azel is quite a bit more expensive right now, but we're hoping, again, with this new release that it will be much more similar to Rust Motoko. We'll see how much more. And then, Motoko probably has some better syntax, right? Like it might be more verbose to do some things in Azel or Kyber or Rust, and it might be an actual syntax built into Motoko. So I don't know. It's like all the languages have trade-offs. Generally speaking, on the Internet Computer, they're all doing the same thing. One thing that you run into with Azel more than others, because of the efficiency issues, is that you'll run into cycle limits more with Azel. So you might have to chunk things up more, or you might not be able to upload as many bytes or do as many byte operations or anything where you have like large arrays of things. So yeah, but I think it all comes down to it's like the efficiency. The key differences might be efficiency, the ecosystem and packages that are available to you, and then maybe like the developer experience of the syntax. So you'd have to weigh all those properties. But for example, Azel is in many ways TypeScript right now, and therefore you get tons of TypeScript stuff right out of the box, whereas Motoko might be less mature with developer tooling and such. So if you have any more specific questions, I can answer them, but I feel like that's a general. Yes, Motoko, I believe,
How do
is
you
fastest.
how do you define efficiency exactly? Like
How the number of instructions, which you
number
put
of
within
WASM instructions?
number of WASM instructions per unit of
Oh,
time, I would say, and then you can convert that into cycles, and then cycles you can convert into actual costs.
yeah.
someone asked, but using third-party packages have vulnerabilities, right? I mean, any code that you use could have vulnerabilities. So, yes.
Yeah, it's valid for NPM packages, but also for Motoko packages in that case.
Yeah, but those packages also could have vulnerabilities. And maybe I'll just give this spiel right now. So, like, I'm not a fan of domain-specific languages. Like, I don't like that Solidity exists. I'm not really a fan of the fact that Motoko exists because I don't like domain-specific languages because of the absolute, like, just the huge amount of friction that it takes to not only learn a new language, but to rewrite all those libraries, to deal with the decades of experience that people already have in other ecosystems and such. So, and then I think so that's just like a personal thing. So obviously other people can have different opinions. But I do think, objectively speaking, there are going to be trade-offs between all these things, and the benefit of using something like Azel or Kybra is going to be that you already know how to use those things, and you already like those communities, and you can use all those materials, and you can use hopefully eventually all those packages. And high-level languages are always more expensive than low-level languages, right? It's like, why would you choose Node.js versus Rust for your server? You choose Node.js because you can hire JavaScript and TypeScript developers, and you can get going super fast, and you can use all those packages. If you always go for the absolute like most secure, most efficient, blah blah blah, then like you would not be using a lot of languages. You would only be using like assembly, basically, right? You'd only be doing the absolute most low level thing. So those are some of my thoughts on choosing. So you have to choose for yourself based on those factors.
Yeah, okay. All right. So
Yeah,
next
you're welcome.
session in 3 hours, mentorship session. And thank you, Jordan, again.
Yep. I'll see you guys.
See you.